Alrighty, in this video we're going to look at solving absolute value inequalities. So, let's start with the absolute value of x is less than 3. Okay, very simply, we're trying to figure out what values of x that when we take the absolute value of those numbers are going to give us something less than 3. Or what numbers are closer than 3 to 0 on the number line. Okay, so let's understand first how our absolute values kind of work. Okay, let's just do this by making a table. Okay, just an XY table. And we're going to go from -5 to +5. This is going to give us help in understanding the behavior of absolute value functions. We're saying if x is -5, our y is going to be our absolute value of x. Okay, and this is going to help us understand what's really going on in these problems. So the absolute value of -5 is +5. Alrighty, that was that. Absolute value of -4 is +4. Absolute value of -3 is +3. Absolute value of -2 is +2. Absolute value of -1 is +1. Absolute value of 0 is 0. Absolute value of 1 is still +1. And so on throughout this table. So let's look at this table. Okay. Well, we see symmetry in the table. Okay, we see we're just increasing after our 0, and we're increasing as well before our 0. And that makes sense because absolute values are just how far away from 0 a number is on the number line, or it makes the number positive. Okay, -3 is 3 units away from 0. -2 is 2 units away from 0. That's why absolute values that we know before are always positive. So we're going to get this kind of pattern in all of our absolute value tables. Okay, they're going to be decreasing, and they're going to be increasing again. Okay, similar to a parabola. These are just kind of strictly linear increases. So, for what values of x are we going to get the absolute value of x that's less than 3? Well, I see the absolute value of x, the absolute value of -3 is 3. The absolute value of +3 is 3. So where are we less than 3? Well, I see that we're less than 3 kind of in between -3 and +3. Okay, our absolute value of x is in between -3 and +3. When x is -2, our absolute value is 2. X is -1, our absolute value is 1. If x is -2.5, the absolute value is still +2.5. So what this is showing us that now we're making a number line. That was poor spacing on my part. Okay, so we're just making a number line. And whenever we have absolute value, whenever we have inequalities, we're representing our solution as a number line, and we're going to look at what is the inequality answer actually going to look like. Well, we saw here in our table that our absolute value of x is going to equal 3 when x is -3 or when x is +3, because that's when x is 3 units away from 0. And if we want it to be less than 3, well, that's in between these two boundary points. When x is any number in between -3 and +3, when we take the absolute value of it, we're going to get a number that's smaller than 3. So this is what we'd shade in on our inequality. Okay, if x is any number in this shaded region, when x is between -3 and +3, when we take the absolute value of it, we're going to get a number that's less than 3. Because we see in this table, these are the numbers that are less than 3. And that happens when x is between -3 and +3. And the way we write this, I hope you remembered, is -3 is less than x is less than 3. Okay, when x is between -3 and 3, the absolute value of x is going to be less than 3. And hopefully that's very simple and intuitive. Okay, looking off the same table, well, what if we have the absolute value of x is greater than 3? So let's make a new number line. Now let's look back at our table. Well, absolute value of x is still 3 at -3 and +3, but where are the numbers that are going to be greater than 3? What numbers are farther away than from 0 than 3 on our number line? So we look at our table here, and we see that now we're kind of going in the opposite direction. So when x is less than -3, and we take the absolute value of the number, it's going to make it something bigger than +3. And if x is greater than 3, we're taking numbers that, when we take the absolute value, they're going to stay greater than +3. So we still have these same two boundary points, -3 and 3. But now if we want the distance to be greater than 3, then we're looking at the numbers over here. The absolute value of 4 is 4. That's greater than 3. The absolute value of 5 is 5. That's greater than 3. The same thing over here. The absolute value of -4 is 4. That's greater than 3. The absolute value of -5 is 5. And that's greater than 3. So we have an inequality or a number line that looks like this. Okay, when the absolute value of x is greater than 3, that means x has to be less than -3, because when we take the absolute value of it, it's going to turn into a number bigger than +3, or x is greater than +3, because when we take the absolute value of it, it's going to stay a number positive, or that's bigger than 3. Okay, and that's it. Now let's just look at these two shapes and have these two kind of representations on a number line, let them kind of sink in. Whenever we're taking absolute values, we're doing absolute value inequalities, we're going to get one of these two number lines. Okay, so when the absolute value of x was less than 3, kind of we had this in between -3 and +3. If we have the absolute value of x is greater than 3, we're going to have off to the left less than -3, or it could be greater than +3. Okay, so why don't you try these two quick and easy ones before we actually get into the actual algebraic inequalities that we're going to have to learn how to solve. So press pause, try these two. It's very similar to the ones we did. You shouldn't have to make a table anymore, but if you need to, go ahead and then press play when you're ready to check your work. Again, you're making a number line and writing an inequality. Okay, so here we're saying the absolute value of x is greater than or equal to 2 now. So again, you can just refer back to this table. Now we're looking at equal to 2. So we have greater than or equal to 2. So that's 2 off to the right, -2 off to the left. So we make our number line. Okay, the only thing different with this one is that we have the or equals to, so we're going to shade in these boundary points. So we want it greater than 2, so we're going off to the outsides. Because the absolute value of -3 is greater than 2. The absolute value of -4 is greater than 2. The absolute value of 3 is greater than 2. The absolute value of 4 is greater than 2. So our inequalities are x is less than or equal to -2, or x is greater than or equal to +2. Okay, this one on the other side, absolute value of x is less than 2. So again, if you want to refer back to the table, here's when it equals 2 and it's less than 2, kind of in between them. So again, we make our number line. Boundary points. Okay, the absolute value of -1 is less than 2. The absolute value of 0 is less than 2. The absolute value of 1 is less than 2. So we have the points in between. So x is between -2 and 2. That's how we write our inequality. Okay, so these are the basic examples to kind of get us warmed up to see how easy absolute value inequalities actually are. So now let's look at slightly more algebraic examples. Okay, stuff that we're going to have to be required to solve. So let's say we have the absolute value of x minus 1 is less than 5. Now we want to look at how to do this without really having to make a table. Okay, so let's try and think through what we did before. Okay, and before we were looking at the absolute value of x is less than 2, so we found when it equals 2, and we realized that that's in between if we want it to be less than 2. So in this example, even though making a table will work, and if you feel like you always have to make a table, that's going to work most of the time until you get to problems where you're going to have fractions and decimals as some of your boundary points. But let's try and think through it the same way we did all the other inequalities. The very first thing we always want to do is find our boundary points. Okay, we want to find when will the absolute value of x minus 1 equals 5. And even though we didn't write this out before, when we made the table for those easier examples we just got done doing, this is actually what we did. We found our boundary points. So we know from before that we're going to get 2 boundary points or 2 solutions because this equals a positive number. Okay, so x equals 6 is one of them because 6 minus 1 is 5 and the absolute value of 5 is 5. And our other boundary point, well, we know x minus 1 could also equal negative 5, which means x would equal negative 4. Okay, this one comes from x minus 1 equals negative 5. And we just add 1 to both sides. Again, I'm assuming you know how to solve absolute value equations very quickly at this point. If you don't, then you need to refer back to an earlier lesson or earlier videos. Okay, so we have our 2 boundary points. X equals negative 4 and x equals 6. Well, the next thing we always did was figure out, or we plotted our boundary points. So we make a number line. Okay, we make it big enough to include all of our, or both of our boundary points. Okay, it's just less than, so these are both open. So if we want the absolute value of x minus 1 to be less than 5, we've got to figure out, are we going to be shading in between these 2 boundary points or on the outside of these 2 boundary points? Now you're going to learn very quickly once you do these problems and pay attention to how the problem relates to the solution, how to just jump to the answer right away. But let's just work through our steps. We want the absolute value of x minus 1 to be, less than 5. So let's say x is negative 3. Negative 3 minus 1 is negative 4. Absolute value is 4. That's less than 5. Negative 2 minus 1 is negative 3. Absolute value is 3. That's less than 5. Negative 1 minus 1 is negative 2. Absolute value is positive 2. That's less than 5. So it seems like all these numbers that are in between, just by substituting them in, is going to make it true. I mean, that's what it is. Okay, 3 minus 1 is 2. Absolute value is less than 5. 5 minus 1 is 4. Absolute value is less than 5. So all of these numbers in between these 2 boundary points are the solutions. And we just did that by testing our points. And that's really mental math. There's really nothing to write down here. You're plugging in values. Okay, you pick numbers in between. If you think it's going to be in between, again, make an educated guess. I thought it was going to be in between, so I picked numbers in between and said, what happens? Is that what I want? Negative 3 minus 1 is negative 4. Absolute value is positive 4. That's less than 5. Negative 2 minus 1 is negative 3. Absolute value is positive 3. That's less than 5. I test all these points on the inside. I could test all these points on the inside, and they're all going to give me something that's less than 5. So this answer is negative 4 is less than x is less than 6. Okay, very simple. Okay, let's do one more together. Let's say the absolute value of x plus 3 is greater than or equal to 4. Okay, step 1, let's find our boundary points. So that means I want to know when will the absolute value of x plus 3 equal 4. Well, that's when x equals 1, because 1 plus 3 is 4. Absolute value is still 4. Now I also know I could get x plus 3 to equal negative 4, because I know the absolute value of negative 4 is 4. So that happens when x equals negative 7. Again, this comes from x plus 3 equaling negative 4. So these are my 2 boundary points, x equals 1 and x equals negative 7. So I'm going to start placing on my number line and testing my points. Okay, they're shaded in now because we have the or equals to. That's nothing new. Okay, now I just got to figure out I'm going to shade in between or I'm going to shade going off to the outside. I don't really know yet, so I'm going to pick a point in between. Negative 6 plus 3 is negative 3. Absolute value is positive 3. That's not greater than 4. Okay, so kind of in between doesn't work, so let's just double check on the outside. Negative 8 plus 3 is negative 5. Absolute value is positive 5. That's bigger than 4. Negative 10 plus 3 is negative 7. Absolute value is positive 7. That's bigger than 4. Let's double check on the right side over here. 3 plus 3 is 6. Absolute value is 6. That's greater than 4. And it takes 2 seconds to check your points, and that's all I'm doing. I'm testing my points. I'm finding where are my solutions. My solutions are going off to the outside. Okay, again, 2 plus 3 is 5. Absolute value is 5. That's greater than 4. That's why this is a solution. That's why we're shading to the right of our boundary point at 1. And negative 8 plus 3 is negative 5. Absolute value is positive 5. That's greater than 4. That's why we shade going out this way. Okay, so our solution is x is less than or equal to negative 7, or x is greater than or equal to 1. Okay, and this is how we write our answer when we have these number lines going in opposite directions. When x is less than negative 7 or equal to negative 7, we're going to be taking the absolute value of a number that's smaller than negative 4, which means the absolute value is going to be bigger than positive 4. When x is greater than 1, we're going to be taking the absolute value of a number that's greater than 4. And that's going to give us a number of greater than 4 because absolute value of positive stay positive. Okay, so try a few on your own. Okay, the absolute value of x minus 5 is less than or equal to 2. The absolute value of 7 minus x is less than 5. The absolute value of 2x minus 5 is greater than or equal to 3. And the absolute value of 3x plus 1 is greater than 7. Okay, so press pause, try these, and press play when you're ready to go over them. Okay, the first one. The first thing we want to do is find our boundary points. Absolute value of x minus 5. When is that equal to? That's when x equals 7 and x equals 3. So we make our number line. Plot our boundary points. They're shaded in because it's or equals to in the original problem. Okay, my educated guess is that it's going to be in between. 5 minus 5 is 0. Absolute value is 0. That's less than 2. 4 minus 5 is negative 1. Absolute value is positive 1. That's less than 2. 6 minus 5 is 1. Absolute value stays 1. That's less than 2. I made a good guess. Again, you don't have to test all the points, but it's good to do so. So when x is between 3 and 7, the absolute value of x minus 5 is going to be less than 2. Okay, next example, my boundary points. I want to find when will the absolute value of 7 minus x be equal to 5. That's when x equals 2 and x equals 12. And I just make my number line. Open circle this time. Again, my educated guess is that it's going to be in between these two because we want it to be less than 5. So I'm going to pick a point. 3. 7 minus 3 is 4. Absolute value is 4. That's less than 5. 7 minus 4 is 3. Absolute value is 3. That's less than 5. 7 minus 7 is 0. Absolute value is 0. That's less than 5. So on. Okay, all these points made it true. Now I'm talking quick, but you should be thinking quick. And you just pick a few points in here, substitute them in, see if it makes it true. 7 minus 6 is 1. The absolute value 1 is 1. That's less than 5, so that's a solution, so it should be in the shaded region. That's all I'm doing. 2 is less than x is less than 12. So when x is between 2 and 12, the absolute value of 7 minus x is going to be less than 5. Okay, the two final examples. First things first, let's find our boundary points. When will the absolute value of 2x minus 5 equal 3? That's when x equals 4 and x equals 1. Okay, closed circle because it's or equals to. Okay, now we want this absolute value to be greater than 3, so my educated guess this time is going to be on the outsides. So I'm going to check 0. 2 times 0 is 0, minus 5 is negative 5. Absolute value negative 5 is positive 5. That's greater than 3, so that's a solution, so it should be in my shaded region. Let's check my negative 1. 2 times negative 1 is negative 2, minus 5 is negative 7. Absolute value is positive 7. That's greater than 3, so that's also a solution, so it should be in my shaded region. So it seems like my guess is correct. Okay, we're shading going off to the outside, but let's double check on the right side. 2 times 5 is 10, minus 5 is 5, absolute value is 5, which is greater than 3, so that should be a solution. It is a solution, so it should be in my shaded region. Let's double check 6. 2 times 6 is 12, minus 5 is 7, absolute value is 7, that's greater than 3, so again, it's a solution, so it should be in my shaded region. Okay, so my guess was correct. We're shading off to the outside. Now I just need to write this correctly. X is less than or equal to 1, or x is greater than or equal to 4. And you don't write anything fancy here when you're going off to the outside. It's x is less than or equal to 1, or x is greater than or equal to 4. Okay, last example. As the value 3x plus 1 has to equal 7. This means x equals 2, or x equals negative 8/3, which is negative 2 2/3. So let's plot these boundary points. Okay, so 2, open circle, negative 2 2/3. Please don't tell me you don't know where that is. And now, my educated guess this time, because it's greater than, I'm going to think it's going off to the sides. So I'm going to check negative 3. 3 times negative 3 is negative 9, plus 1 is negative 8. Absolute value is positive 8, which is greater than 7, so that needs to be in my solution region. 3 times 3 is 9, plus 1 is 10. That's absolute value stays 10. That's greater than 7, so my 3 has to be in my solution region as well. This is exactly what I expected. We're going off to the outside. X is less than negative 3. Or sorry, not negative 3. X is less than negative 2 2/3, or x is greater than 2. Okay, and that's it. So if you need more examples, still refer to some of the other online resources or the packet of the textbook.